Okay, so we are now in the last few talks for today and for the meeting, and those talks will be about two very important tools that we use in our day-to-day life to help people with finding a baseline of performance and tuning, like Gert introduced in his tutorials. And the first talk will be from Mark Miller, our long-term user supporter and HDF5 advocate, about MACSio, parallel IO proxy application, and HDF5 plugin. Mark, it's yours.
Thanks, Elena. I have my video on right now, but if I run into network problems, I will probably turn it off. And thanks to the HDF group for setting up this users group, and hope to have and be able to participate in more of them. So I'm going to talk about MACSio. That's multi-purpose. Well, I'll describe what MACSio stands for. What is it? It's a multi-purpose, application-centric, scalable I/O proxy application. And I'll just kind of go into what I mean by each of these things. Multi-purpose means that I think it's highly flexible in the kind of I/O workloads it's able to emulate. It's application-centric, and that it works at a high level of abstraction for the kinds of, the way it thinks about data is that as scientific objects at subsense, not as sort of buckets of opaque bytes or arrays. It's focused on supporting a variety of parallel I/O workloads. We'll talk about that in a little bit. And finally, it's a proxy application. It's more than a benchmark. So it aims to represent realistic workloads from real HPC applications and to enable comparisons among various approaches. Why was MACSio developed? It was actually started development in 2016. The existing tools available at that time didn't really operate at the level of abstraction that I felt a proxy application needed to. There were basically two types of things that were available at the time: benchmarks and application kernels. And those two types of software had various limitations as far as the kinds of I/O workloads that it can support and flexibility. So bottom line, just to emphasize, MACSio has a lot of flexibility. I'm just going to spend a few slides talking about I/O abstraction in the HPC I/O stack. I'm not expecting you to read this code, but using as an example an application that needs to write image files, for example. If you're working at the low-level I/O interfaces of the system, you might end up with code that kind of looks like this, where you CD into a directory. This is C code. You know, do some opens and writes of raw header information, such as maybe the size of the file in X and Y and what the fill value is, and then stop at a barrier there. And then each processor opens the file independently and does a p-write to it and close, for example. Very, very low level if you're only thinking about the data in terms of bytes and getting bytes to disk. If you start to think about it at a little bit higher of abstraction and maybe trying to use parallel I/O tools to do it, then you end up with a slightly different bit of code. Also, basically reading, writing here still bytes to files on the underlying file system. But ultimately, our applications think about their data in terms of scientific objects. They have meshes or images or fields defined on meshes or time series or whatever those things happen to be. And so you often have a much higher level interface that the application interacts with. In this case, it's an image database interface. Each processor is going to open that database. It's going to put its piece of the image and then finally close the image in the image database. The point I'm making here is that there's this sort of layers of abstraction involved in taking these high-level scientific objects, for example, the pressure field over a airplane fuselage or wind flowing over a truck, for example, and then ultimately writing it down to these devices, which are these low-level storage volumes. And that abstraction, you know, layer, you can get as detailed or as coarse if you want, but basically I'm trying to characterize what all the different layers of abstraction are in terms of the kinds of objects that the applications write out. Right here in the middle of that stack is things like arrays and structures and lists and trees, the kinds of things that you might think were typical to write to an HDF5 file. But above that, you get into things like meshes, partial differential equation fields, topologies on manifolds, and then finally, maybe you're writing out physics data, chemistry data, you know, bio data, neurological data, whatever. This picture is almost identical to what you see in the IP protocol stack. There's a layers and layers of abstraction on top of the IP protocol stack, and each of those layers has various levels of overhead associated with it in terms of header information that may be needed to manage that particular level of abstraction. The reason that this stack concept is just really important is when we talk about I/O, it's important to talk about where you're operating at within the I/O stack, the level of abstraction stack. And so I'm just trying to actually here, I won't go into detail here, but just trying to describe some more of the conceptual stuff on the far left and then actual software implementations you see of this kind of stuff on the far right. But if you look at a lot of the existing benchmarks and I/O performance tools that are out there, they tend to operate down here where this blue arrow is pointing, the file system, POSIX I/O interfaces or MPI file I/O interfaces. And the point is that, oops, sorry, I'm going backwards there. That's where existing tools tend to operate, and MACSio is designed to operate at a much higher level of abstraction. And I think that's important because there are I/O performance issues that can occur as you trickle data down through these different levels of abstraction. And I'll refer back to, you saw, I think, some of the slides that Greg Jardama presented earlier in the day. You saw this layering of software and what he was talking about, where you had IOSS on top of CGNS, on top of HDF5, on top of MPI I/O or something like that. At the time we started to develop MACSio, we looked at a number of other tools that were out there. I won't go into this slide in detail, but this is an attempt to codify some of their attributes. For example, the level of abstraction they operate at, what parallel file modes they support, and I'll talk about these more single shared file or multiple independent file. Whether they support collective I/O operations, whether the data that they marshal is realistic in some sense. Writing buffers that are all zeros or all ones, or buffers that are garbage data are not really useful. If you want to test compression algorithms, for example, it's important that the data represents something real. Whether the particular technique that's used preserves the abstractions. That as you go down through the I/O stack, the question is, do you preserve the abstractions? Just marshaling data to bytes on disk is one thing, but if you're sort of required to preserve the abstractions in that process, that comes with additional overheads. And if you're not taking those overheads into account, then you're not fully measuring what the I/O issues are. So I won't go into what the other columns are here, but basically we looked at a number of existing technologies and decided it had some sense of what their strengths and weaknesses were, and then started developing MACSio. So a key aspect of MACSio is to support flexibility in parallel I/O paradigms. I'll talk about three of them here. One you've heard, probably seen many times, and it's basically file per processor. And that's where every processor opens its own file, writes data to disk, and closes. Obviously, when you do this from, say, 1 million MPI ranks or 100,000 MPI ranks, it's a lot of files. You can overwhelm the lesser file system with a lot of file metadata. But it turns out this technique is super effective, even at moderate scales, and is still in use today. And if the other parts of your workflow are designed to support it, it actually works quite well. And if you'll notice, if you remember, a lot of Greg's slides where he showed performance, this sort of benchmark question was, can we do better than this mode of I/O? So that's file per processor. Multiple independent file is a little bit different than that. In multiple independent file I/O, what you do is you break the set of processors into different groups. In this case, in this example, there's two groups here. The red, blue, green processors are in one group, and the yellow and orange processors are in a different group. And each group writes one file. And what you have is serial access to the file within that group. That's basically round robin. They're passing a baton to access the file. But both groups are writing a file independently, so it's concurrent across groups. And the number of files that you produce and the number of MPI ranks or processors are completely independent. They're completely decoupled from each other. In fact, file per processor is just a generalization of this technique where the number of groups is equal to the number of processors. That's often called N-to-M. And then finally, single shared file, all the processors are basically trying open and using either collective or independent I/O requests to a single shared file. Okay. I can talk about some of there's a number of sort of variations of these key parallel I/O paradigms, whether or not you're reading and writing to burst buffers, or burst buffers are a part of the architecture that you want to take advantage of when you're trying to marshal data between memory and disk. whether you're doing collective versus independent IO operations. The IO is segmented versus strided. To some extent, that has to do with how interleaved the IO operations are from different processors. If they're largely non-interleaved, that's more of a segmented approach. And if they're highly interleaved, then it's more of a strided approach. Whether or not you use two-phase IO, that there's some process of collecting data from multiple ranks, and those collectors then turn around and write the files. Knowing about the IO node affinities on the machine and so forth. So there's a number of swizzles on how to do these various parallel IO paradigms, but these three main paradigms are the ones that we tend to be interested in. So I'm going to talk about multiple independent file in detail on this slide. Up here in the upper right is a graphic where we have 6 MPI ranks. Those are the blue boxes. We have 3 groups. Those are sort of the maroon boxes. And the mesh, the parallel decomposed object in this case is a scientific computing mesh composed of 16 domains. And those are sort of these orange pieces. And you'll notice some tasks have 3 domains. They have a little bit more data than other tasks that have 2 domains. Each group writes its own file. So there's 3 files that come out. And first task 0, task 2, and task 3 open the initial files, file 0, 1, 2, 3. They write all their data to disk, and then they close the file and hand it off to the next group in their task. Task 4 basically opens it file after task 3 and so forth. The point of this approach, again, it's concurrent across groups, but it's serial within groups. The number of files is totally independent of the number of MPI ranks. You can, if you wanted to, you could dial it all the way down to just 1 file for the whole thing. And if you do that, that's equivalent to serial IO, so not very effective. But nonetheless, for small numbers of tasks, say 16 tasks, it's quite a useful thing to do if you want all your data in 1 file, and you don't really care about IO for performance, for example. Another thing is you can change the number of ranks from run to run. In this case, we have 16 mesh pieces, so we could run on a number of processors anywhere between 1 and 16. And the process of marshaling the data around looks the same no matter what number of processors you run on at the end of the day. Concurrency is ultimately here managed by the application. We're not delegating concurrency to the underlying layers in this IO software stack. The application is managing concurrency. Ultimately, the software, the code that developers need to write to do this is very simple. In particular, when you're writing data from one processor, you don't have to be sort of shackled with the needs of a collective interface that may have different types of data on other processors to write out and have that all work through a collective interface. Finally, this all works with a serial IO library. You don't need any special functionality from the library to make it do it. It has simple throttling. Very easy to throttle the total number of tasks that are actually doing IO at any one time. And it's equivalent ultimately to the kind of stuff you see in big data, for example, MongoDB shards. So that's MIF in detail. Now I'll sort of return back to talking about MACSio, how it operates. So you've heard me talk a little bit about meshes. What MACSio does at the end of the day is it basically has, and by the way, Elena, how am I doing on time?
You have 7 minutes before next talk.
Okay, thank you. So we have an Uber JSON object we create in MACSio, which describes the mesh, the global aspects of the mesh, and then all of its parallel decomposed pieces. Each MPI rank, of course, only instantiates the parts of the mesh that it owns, but it's all characterized as an Uber JSON C object. And so the way that MACSio is designed is you have an upper level sort of main that's responsible for creating the data, and then a lower set of IO library plugins. And then the MACSio main basically passes that Uber JSON object onto the plugins and say, write that data. And so there's a mesh and field data generation. There's a parallel IO mode manager. There's some functionality to deal with file system operations, such as creating directories, seeding into them, sequencing the read and write operations. And then there's this burst write operation. Write this JSON object to disk. That hands the JSON object off into a plugin. Plugin writes it. Likewise for read, the plugin reads it and then instantiates that JSON object. There's some timing control and event logging that's going on. And then there's various IO libraries that you can write to, HDF5 Exodus Silo, Some you probably haven't heard of here, and stuff in red actually isn't yet developed. It was planned when I put these slides together, but I haven't actually developed a MFEM or libmesh plugin yet. Neither are trickle reads and trickle writes. Those are kind of important because real applications tend to write bursty data, but they also tend to trickle stuff out as well. That actually is implemented now, but I discovered a bug in it just yesterday. So that's the overall architecture. And again, the HDF5 plugin that exists in MACSio right now, it supports multiple independent file and single shared file, collective or independent IO. It supports a number of different compression methods, deflate and SIP, which are built in, ZFP, which is a operator, is a plugin. I could say some more aspects of the HDF5 plugin, but I wanted to take just a moment and talk about the use of HDF5 at LLNL. We've used it since 2002. It's a middleware underneath Silo, so it's in the middle of that abstraction stack. We use it for multiple independent file per time step. The same software runs on that runs on the LCFs, the really large systems at 1,000 or 100,000 cores, runs on my laptop. It's exactly the same software, and allows me to develop on my laptop too. Data is decomposed form. There's never this process of, you heard Greg talk about joining or decomposing. In the workflows we have, all the software is designed to basically just manage the data in all its different pieces. At the end of the day, HDF's been very successful at Livermore. We've used it and we've had a number of successes with it. And that primarily has to do with number one, the technology, but also the THG staff and collaborators have been instrumental in the success of HDF5 at Livermore. I think I'm just gonna, this slide was intended to talk about all the cool features of MACSio. It does have a lot of cool features as far as what it can represent, but I'm gonna basically go through that very quickly. We ultimately use MACSio to diagnose and ultimately fix some memory performance issues. So I'll just, this is actually from 2016 or maybe even 15 at the time, but we had peak memory issues that were going on in HDF5. I think this was on 1.8. Ultimately got a contract with THG to turn around and fix those issues. So that future column is actually what currently exists now with Silo on top of HDF5 as far as peak memory usage for a particular use case we were studying. Okay, so the final, well, second to last slide, when you generate data with MACSio through its plugins, the reason it needs to look realistic, and this is an example of it. So this is MACSio data being visualized in Visit. It's written it to Silo in this case, and you can see the domain decomposition here, a spherically symmetric variable that was written out, and then some variables, two different variables with different types of noise. And I show these to demonstrate that the data looks kind of realistic. And this is from 4 processors running 10 parts, a mesh decomposed into 10 pieces. This is on 2048 core run, the same thing. I'll skip that slide. Information on where you can get MACSio. And I think that's it. My apologies for going so fast. I realized I had a couple of slides I went into too much detail on. So I'm done.
Thank you, Mark. And we have 2 minutes for questions.
If there are no questions, I will go back and make two quick remarks.
Sure.
Sorry. So just on this slide here, HDF5 has been successful at Livermore because of the abstractions that it's provided. Several years ago, we had a problem with file system. Our file system, the hardware in the file system was actually corrupting data, and nobody was aware of it. And the question is, what do we do about it? We were talking about millions of dollars to basically try to address the issues in the hardware. Ultimately, we added checksumming to Silo, which uses HDF5 as an application level checksumming as a stopgap to make sure that we would at least be aware of corruption when it was occurring. And that was hugely successful, didn't take any performance costs, and ultimately saved us from running for several months with a file system with corrupted hardware. We've had a number of other successes with using HDF5, for example, 50x performance proven when we developed our own virtual file driver. So I just want to emphasize those successes are possible because of the close collaboration that we have with THG and the developers at THG and their collaborators as well. So I just wanted to, others have made that point and I wanted to jump on that bandwagon.
Thank you. Thank you. And you may still ask Mark and chat window about, this is a really cool piece of software. And if you want to find baseline and understand, this is a good way to start with HDF5